Okay, so yeah, so maybe we can get started. So okay, so first of all, so we should finish the martingale convergence discussion. By the way, I did make a mistake in the last lecture about the definition of super martingale and sub martingale, which is I would say confusing, but the terminology is standard by now. So the definition is that a process, a sequence of random variables xn is a sub-martingale so we have to compare the expected value of xn plus 1 given x1 xn. So the value in the future, given the values in the past and today, with the value of today. Right? And in fact, the actual inequality that defines the sub-martingale is bigger or equal. So in fact, sub-martingale means that the expected value of tomorrow's value of the process is bigger or equal than today's value. So I think the reason why we call it sub like this is because there's an interpretation in terms of subharmonic functions. So, yeah. And the super martingale is the opposite. So last time I gave the opposite notation, which is wrong. At least, yeah, this is not the well-known traditional convention. So sorry about that. Okay, so once you do get this definition, then you have the martingale convergence theorem that we mentioned already last time. So the theorem, which is due to Doob, so Doob's martingale convergence theorem. Well, basically, in words, it tells us that an integrable, either sub-martingale or super-martingale, converges almost surely. And if you want to do slightly more general condition, you can just ensure the integrability sort of the positive part or the negative part. So in fact, the correct way to say is like this. So suppose, yes, so suppose that xn is a sub-martingale with the expectation of xn plus, so the positive part. So if this is uniformly bounded, so this is, yeah, so this is less than c for every n. So there exists a c such that the integral of the positive part is bounded above. Then this is enough. Then, yes, then there exists a c. Then there exists a random variable. There exists a random variable x infinity such that xn converges to x infinity almost surely. So in fact, going back to the fact that, yeah, comparing, so now it makes sense that this is the right condition, because now we're doing the upper integrability. We have to assume that, and with this definition of sub-martingale, then you would see that, you see, in a way, the expectation of xn goes up. So expectation of xn plus 1 is sort of bigger. So in a way, this condition would provide some sort of lower bound. So you have to assume the lower bound, and the other one sort of comes from this condition. And of course, the other version is corollary would be that if, on the other hand, xn is a super martingale, with again the expectation of xn minus bounded, so the supremum over n, then there exists x infinity such that xn converges to x infinity almost sure. I mean, this is obvious. It's just to take negative. So in particular, in fact, what we care the most about is martingales itself, not super martingale or sub martingale. So then either way, it's fine. In particular, most of the time we were just going to consider in this course just bounded martingales. So if the supremum is just bounded everywhere, then we have no problem about integrability conditions. Okay, and so as I said, the remark that I already said last time is that, well, this does not assure, this does not imply that xn converges to x infinity in L1. Yes? Yeah. Yeah, I think it sort of follows from this. Yeah.
But then if the positive part is bounded,
Yeah.
that's the same as
Yeah, that's right. That's what I'm saying. Like, yeah, I think if you assume this and you assume the super martingale condition, so maybe you want x1 to be an L1, yeah. Yeah, all the time we're going to assume that it's an L1, but I think this should be enough. Like in the ergodic theorem, I think you only have to assume that the positive part is integrable, because it could be that the limit is negative infinity, which is kind of a not very nice case. But I think you would still get. Yeah. So, but most of the time, most of the time we absolutely, yeah, we just assume that xn is an L1, so it's not. Okay, so this is a theorem. So I don't want to give a proof because we've seen already proofs of other similar theorems before. But it's nice we can see some applications. So for instance, applications, well, the first applications that we can see is about the recurrence and or transients of random walks on trees, and in particular on radially symmetric trees. So what is a radially symmetric tree? It's just a tree where the number of children of the tree of each node depends just on the distance from the origin. So it's like that. So let me say the following. So you have, so given some integers t, a1, a2, an, so sequence of integers. With, let's say that each an is bigger than 1. Okay, so the radially symmetric tree, the t of a1, a2, an Okay, so this radially symmetric tree is, yeah, it's basically is a rooted tree. It's a rooted tree where, yeah, the nodes at distance n from the root have an children. Okay, so in fact, maybe, yeah, maybe we can start with a0. Maybe it's even better here. Okay, and so what? So for instance, what do we have? So let's do T2, 2, 2, something like this. Is just a binary tree, so it has 2 children, then 2 children, and 2 children, and so forth. That's
For this n fixed, or the like mean for all a and
yeah. These are infinitely many n's, right? Yeah. Or then, yeah, for every n. Yeah. What's wrong with it?
I was just confused to go like an as one of the specific elements.
Yeah, because you can change. If you do T2, 3, 4, 5, something like this, this would mean what? You have 2 children. Each of them has 3 children. And each of them has 4 children. Like that. Okay, definition? Yeah. Okay, good. So the question is whether this if you do simple random walk on this tree, so every time you choose one of the neighbors with the same probability, then would this random walk be transient or recurrent? Okay. And so it's kind of neat. You can sort of predict that using martingales and some sort of harmonic functions that we haven't seen in general yet, but I think it's a good warm-up exercise. So the thing is the following. The theorem is like this, that the simple random walk on this T of A0, T A1, blah, 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 is recurrent. Well, if and only if basically the sum is transient, if and only if the sum is fine. Yeah, so if and only if you take the sum of 1 over A0, A1, AN from n equals 0 to infinity is finite. So basically, you take this series, which is a series of positive numbers, and it could converge or diverge. And well, in the end, you check whether the series converges. If so, then the random walk is transient. In fact, as a corollary of this, it's almost always transient, because what do we need to do in order to make this recurrent? Right, this series, remember that these AIs are numbers, are integers, right, bigger or equal to 1. So we really don't have too many choices to make it recurrent. How do we make it recurrent? Right, so we have to put Yeah, exactly. So infinitely many once is enough. And let's see, is it need? Yeah, is it the only thing that could happen, right? So let's see. So yeah, so let's see, right? So in fact, if the simple random walk is recurrent as a corollary, well, definitely we need to have, there are infinitely many n's such that an equals 1, because otherwise there have to be at least 2, and then you would have a geometric series. So obviously, if you put all ones after some time, then it's recurrent. Is that the only thing we can do? Can we still make it recurrent when there's infinitely many 2s? Why not?
When there is infinitely many 2s and finitely many 1s, or just
no? Let's say we have infinitely many 1s and infinitely many 2s.
I mean, you could just consider the series of just the 2s and they'll still. Right? Or maybe not.
It's a good question. What? Sorry? Right. So let's see, right? So suppose I give you t of, okay, I put a lot of 1s, then I put a 2, and then I put a lot of 1s. And then I put a 2, and then I put a lot of 1s. Can I make this diverge? Yeah, right? So if you put 2 to the n, yeah, so these are, yeah, let's say 2 to the 0 or something, 2 to the 1, 2 to the 2, right? So if you put 2 to the n, so if you put 2 to the n once, and then from time to time at 2, right? So then what would happen to the powers? Well, okay, you start with 1, you get 1, right? So in between, let's say that you put 2, and then you put 2 to the n once, and then you put another 2. That. So what happens in between here, right? Whatever you had before, you have it 2 to the n times, right? So yeah, exactly. So in this case, yeah, if you, yeah, basically you could say, okay, maybe let's even start with 2. That maybe is easier to deal with. So you have blocks like that, right? So then this would be what? This would be 2. How many times you have 2? Well, you would have, yeah, you would have it how many times you have here. So in general, you would have this one, you would have 2. How many times you're gonna have it? Yeah, you're gonna have it 2 to the n plus 1 times. Yeah, and so this I think would still diverge. Yeah. So in fact, there is a way to make it still recurrent if you bifurcate very, very rarely, and then you go like in a straight line, and you bifurcate, and then you go in a very, very long straight line, and then you bifurcate again. Yeah, so it's not completely trivial, but still there are not so many options. Yeah. Okay, so now let's look at the theorem, and the theorem will use some result on Markov chain, and which also will use some of the martingale conversions. So we need some lemon like this. So lemma, which is due to Blackwell, which says the following. So consider the Markov chain on just the integers defined like that. So P of 0, 0 is 1. So if you're at 0, so P 0, 0 means the probability of going from 0 to itself. So it's 1. So it's a Markov chain. What's a Markov chain? You just have a set of states, which is, in this case, is just the integers. 1, 2, 3, 4. So you have countably many states. And then you have a probability of moving from one state to another state, right? And so we define it like this. So the probability of going from n to n plus 1, we call it Pn. And the probability of going from n to n minus 1, we call it Qn, which is 1 minus Pn. So this is for n at least 1. So basically, this Markov chain, you have a sequence of, you have some numbers. And then, okay, you have a probability of going forward. We call it P1 here. And Q1 is the probability of going backwards. And so forth. So if you're in 2, you have Q2 and P2 and so forth. And so this is Q3. And this is P3. So you have some sequence of numbers like this. And now the question is this Markov chain recurrent? So again, for instance, do you hit 0, for instance? So if you're in 0, you stay in 0. So that's kind of, you don't do anything. But the question is, if you start from some other point on the line, are you going to eventually hit 0 or not? Right? And the theorem is the following. Then the Markov chain hits 0 almost surely, so with probability 1. Well, starting from any n, if and only if, and this is yeah, you see that the condition will be related to what we will call harmonic function. So if you have the following equation, so the equation is like this. The equation is f of n equals Qn f of n minus 1 plus Pn f of n plus 1. So this is an equation. So you're given the coefficients Qn's and Pn's from this model. And now you're asking other solutions of this equation. So can we find some function f that satisfies this? So this is for every n. So if this equation has no non-constant bounded solutions. So you see, we start with a random process, and here we come up with some sort of discrete differential equation, so to speak. So we want to say that if the walk is transient, meaning that you're not going to hit 0 almost surely, then you can find a non-constant solution to this equation, and vice versa. If you find a non-constant solution for that, then it means that this chain is not recurrent. You can escape. Okay, so the proof is kind of neat. So it gives good ideas of how to relate these two. So okay, maybe there's one, I guess maybe one direction is slightly more intuitive than the other. So what is the connection between these two things? right? So suppose I give you this chain. How do you construct a function that satisfies this equation? Any ideas? So you see, this is a function.
Should be the average of
This is a function from n to r or to 0, 1. Yes, what? It's not quite the average. Yeah.
Can you do it? Can you do like x0 f1 and
Well, once you have this equation, you can inductively write it. But what I want to say, the key point is, once I give you this system, so you can run this Markov chain. So, and you want, so can you produce from this system a function on the integers that satisfies this equation? It's, that's exactly right. So you consider the, yeah, this is the most important point. So you consider the following function, f of n, which is the probability of hitting 0 starting from n. So probability is definitely a bounded function. So that's good. And the other thing we have to check is whether this satisfies the this equation star, right? So yeah, why does it satisfy the equation star? Well, it's sort of what is what this dynamics does, right? So you have n minus 1 and n plus 1. So you have Pn and Qn, right? And so, of course, well, what's the probability of hitting 0? Well, you see the probability of hitting 0, hit 0 from starting, given that x0 is n. Let's say x0 is the first step of this chain. Well, you know, you can go either you can either go left or go right, and then, of course, then the probability is, well, it's the probability of, you know, you go from n to n minus 1 times the probability of hit 0 starting from n minus 1 plus the probability of going from n to n plus 1 times the probability of hitting 0 starting from n plus 1. That's kind of what the definition of a Markov chain is. Right, so this equation satisfies star. So clearly, if the Markov chain is transient, then what do we know about f? Is it constant? It cannot be constant. Why? What does it mean that it's transient? It means that starting somewhere, you have a full probability of going to 0. At some point, there is certain escape probability, right? And so this would imply that f is not constant. Then there exists n0 such that f of n0 is strictly less than 1. On the other hand, f of 0 we know is 1, because the probability of hitting 0 starting from 0 is 1. So this is f of n. So f is not constant. So yeah, so that's kind of cool actually. Now the opposite is using the same idea, but we have to be a bit, yeah, I mean, we do need to use the martingale's convergence. So now let's look at, yeah, so how about the opposite, right? So now suppose I give you this function. Suppose there is a solution. Suppose f is non-constant. Solution to star. Right? And by the way, we can normalize because remember that the space of functions that satisfies this equation, well, clearly it's a vector space. And the constant functions are in that space, right? So we can normalize. So adjusting, so replacing f by f prime, which would be a plus bf, where a and b are real numbers, we can assume, well, yeah, we can assume that f, right, so f of 0 is 1 maybe, which is good for this interpretation. And also maybe we can assume that it takes values from 0 to 1. It doesn't really, yeah, to be honest, it doesn't really matter. And yeah, so right, so the image of f is contained in 0, 1. It's bounded function, so you can. Okay, and now we have to show that from this, we want to show that the walk is transient. The walk does not go to 0, almost should. So we want to show that the Markov chain is transient. Okay, so what's the idea here? So we can run, so we have a function now. This function is not a probability function, it's just some function. But we can run the chain, right? So for instance, what happens, so think about this. So suppose you have this chain. Okay, you're running this chain. So suppose, for instance, that this walk, this chain always converges to 0. What happens to the value of f once you're running the chain? It's going to 0, right? So yeah, it's going to 1, the value. Yeah, exactly. Right. So because if with probability 1, the limit of xn is 0, right? Then f of xn also goes to 1, almost sure. Right? Okay, so, but then the limit, yeah, we have to see what is the limit. So how do we relate this? So how can we show that this limit exists in the first place? Well, to do that, we should use the martingale convergence theorem. So the claim is that f of xn is a martingale. Where xn is the market chain. So why is that? Well, we have to do the expected value of f of xn plus 1 given the previous history. Right, given f of x1, f of xn. And so now why is this a martingale? Well, we want to show that the expected value of f of xn plus 1 is the same as f of xn. And I mean, what's the intuition? The intuition is that with certain probability you go to the left, but then you encounter f of n minus 1. And then with certain probability you go to the right, but then you encounter f of n plus 1. And then, but on average, the average of these two values is still this way. Right? Yeah, so that's exactly what it is. So yeah, so this is what? So this is basically is f of xn plus 1. That's the probability of going from xn to xn plus 1 plus f of xn minus 1 times the probability of going from xn to xn plus 1 with xn minus 1. And so literally that's literally what it is, because this is f of x. So we can basically formally what you do is you condition on xn. Xn is some number k, and then we apply that for n equals that particular k. So this is p. I guess we call it p. Yeah, p xn plus f of xn minus 1 q xn. Or maybe it's not so visible, it's not there. Okay, I'll avoid it. Right. Okay, other questions so far? Yes. This one? Yeah. So okay. So what's the idea here is that we're conditioning on knowing the first n outcomes, right? So in particular, we are conditioning on knowing xn. Yeah, knowing f of x1, f of xn is technically a bit less than knowing xn. But okay, let's skip over that little. But in general, if you look at the excitation given the sigma algebra generated by x1, xn, then you can assume that you can condition on knowing the value for xn. Right? And now once you know the value of xn, well, what is the value of f of xn plus 1? Right? Well, it's, you have two options. Either you go from xn to xn plus 1, or you go from xn to xn minus 1. Right? And then you get this. Yeah, so here we're doing the, so we have conditional, we condition on knowing xn, the outcome. Yes? Yeah, this is a bit annoying. I agree with you on that. The thing is, yeah, in the end, you should have a space of functions which is large enough that separates all these variables.
So So are you claiming that f of x1 and f of x2 is also called one function?
Sorry?
Is f of x1, f of x2, all of those the sequence of when f applied to it, is it still going to be a one function?
Why do you need that?
Because the calculation afterwards depends on, this.
Right. So for sure, if I, yeah. Yeah, do you agree on this calculation? Yeah, that's good. So so here's a technical issue, because if you, if we condition only, f, for instance, f could be constant, right? So you want to make sure that knowing f of x1, f of xn is the same and knowing x1, xn. So I agree with that. Yeah. But so I think that the way you get over this trick is to say that you know this for f for sufficiently many functions f that can separate this. Okay, so now what goes on there next? So what's the next step? So the next step is that we know that this converges because this is a this is a martingale. Okay, so so now by the martingale convergence theorem, the limit of f of xn equals f infinity exists almost surely for almost every path, right? So now f infinity is another function so now so now the issue is, so if the Markov chain is recurrent, then then f has to be constant. So because then f infinity equals f of 0, f of 0. So is constant. So the other slightly things that you have to check here is that if f is not constant to begin with, then f infinity is also non-constant.
How do you know that martingale?
Oh, we proved it.
I don't understand why that.
Why? Why not? What do you mean?
So the statement is that the expectation so that expectation is that time.
Yeah, it is by the this guy.
Okay.
This is equal to f of xn by the equation star, which I erased, but it's is the equation that so that's the point. Like the average value of f along the path is constant. That's right. Yes. Now, in the end, there is a little issue here still to verify that I'll leave you to verify it maybe as an exercise. So, I mean, basically the idea is the expectation of f and the expectation of f infinity should be related. And so in the end, if you start with a function on this graph that is non-constant, then we know by the martingale convergence theorem that running this limit procedure will get you a function which is also harmonic, and in particular, so in particular, this will give you a function that would be constant if the market chain is recurrent. But since we started with some function which is non-constant, and the limit will also be not constant, and so from this, you would say that the market chain is constant. Yep.
So for the forward direction of this proof,
Yeah.
we chose F to be the probability that it visits 0, 0.
Yeah.
I was expecting sort of the converse to be the proof of the converse to be you start with an arbitrary. So I guess the question is it true that starting with an arbitrary harmonic function, you can think of it as, or it's in some sense maybe close to the probability that you visit certain points, or is there a converse to the
So if f is the probability,
so if the probability that you visit 0, 0 is a harmonic function,
right?
is there some sort of a converse of this sentence that if you have a harmonic function, you can think of it as you can think of it as the probability that you visit a certain point, or
Well, it depends on how many harmonic functions you have, right? So in general, you have a lot of harmonic functions. So, but yeah, I guess it's kind of true that you can think of it as being a linear combination of probabilities of visiting the different sites on the chain.
Is there a statement of the form that the probability of visiting different sites is a dense subset of the space of all harmonic functions or something like that?
Well, this is kind of related to this Poisson boundary theory. I mean, in the sense that Poisson boundary theory tells you that if the geometric boundary is the Poisson boundary, precisely tells you that you can pick every boundary point, and you look at basically this probability of convergence there. And so you say you look at the Radon-Nikodym derivative to be precise. But anyways, so yeah, you can, for each boundary point, you can construct a harmonic function. And these functions are indeed dense in the space of whole harmonic functions. So that statement is basically true, actually. At least when you.
Can you say this?
Yeah. No, I'm saying that if you are in a situation where, so the problem of the Poisson boundary is kind of very closely related to this. It means that if the geometric boundary is the Poisson boundary, it means that for every boundary point, you can construct a harmonic function, which you can always do. But the question is, are all these harmonic functions that you construct using boundary points, are they all of the harmonic functions and in a suitable sense? So I think in good situations, what you say is true, but yeah. And probably it's also true in this case, but I haven't thought about it for long enough to, yes?
Can you prove the check by using like maybe?
Yeah, that's not a bad idea. So you have a proof in mind?
Yes, expectation of Einstein, that limit is also equal to expectation of infinity.
Let's see. So the expect so what do you want to say? You want to say the limit of the expectation?
Yeah.
Yeah. Yeah. Expectation of f infinity is equal to 1.
on the ball that one. On the condition average is 0, 1. This implies that I'm sending this to.
So you want to say that the integral of this is 1 or something. Yeah.
Yeah.
Yeah, I think the argument is yeah, I think this is part of the proof. Yeah. So yeah. So yeah, think about it. But I think that's a good starting point. Yes. Okay, so let's see, what time is it? 10:52. Okay. So, well, since we're here, maybe we can yeah, we can finish this half of the discussion, like by seeing how this lemma of Blackwell implies the convergence or recurrence and transience for radially symmetric trees. So the issue here is the following. So, okay, so application to radially symmetric trees. So now we have T, A0, A1, and so forth, AN. And we want to construct, so we have this tree. So let's say, yeah, this is A0, A1. So A0 is equal to here, equals 3, A2 equals 2 here, for instance. And we want to construct a Markov chain on N. Well, it's pretty clear what you do now. You take the distance. So we sort of, it's like we're collapsing the tree to just a half line. So you have 0, 1, 2, 3, 4, so forth. So, and now, so we define a Markov chain. So we define again dn, which is the distance between the end step of the walk, which we always denote as Wn here, is the random walk on the tree. And here we call Xn the Markov chain. So the probability of the distance between Wn and 0, sorry, not the probability, just the distance itself. So this is a Markov chain on N. Yeah, we start with the random walk on a tree, and I can construct a Markov chain on N. And the way is you just look at the distance, right? So at each step, instead of recording the position on the tree, you just record the distance. This is a number. And so you're somewhere on here. At least if you're not at 0, because, okay, the way we set up the Markov chain before is that if we are at 0, we go back. But yeah. So we are somewhere on the tree, and we're recording. So we are somewhere here on the tree, and we are recording the distance, and so this corresponds to moving along this tree. Yeah. And so we want to say that we need to check whether there are solutions. So what is Pn and Qn? So Pn and Qn. Well, if you remember in the previous model, Pn is the probability of going forward, and Qn is the probability of going backward, right? So you see how many children there are here. So I think of going forward there are. So Pn is, I think, An over An plus 1, because in total there are an plus 1 children. I mean, children and the parent. So these are the all possible positions. And then Qn is, yeah, Qn is the remaining one where you're going backwards. So it's 1 over an plus 1. Right? Okay, and now we just have to test whether there is a solution to that equation or not. So we have to test. The equation is f of n equals 1 over an plus 1, f of n minus 1 plus an over an plus 1, f of n plus 1. And the question is, does it have non-constant bounded solutions? Right? Okay, well, this is becomes calculation, right? So the trick is like that. You consider delta n to be f of n minus f of n minus 1. And then we just have to rewrite that in the appropriate way, right? So this is what? So this is an plus 1 fn equals f of n minus 1 plus an f of n plus 1. So we bring that f of n. We bring the f of n on the other side. What we're gonna get f of n minus f of n minus 1 equals an f of n plus 1 minus fn, right? And so, yeah, we bring an down here. So this just means that delta of n over an equals delta of n plus 1. So that's not so complicated. And so we can write finally the equation here. The equation is like this. So we say that, yeah, what is f of n? Well, f of n is f of 0 plus the sum of delta of k for k equals 1 to n. And now by induction, you can see that delta k is 1 over a 0. Okay, right. So from here, you see that delta of k is 1 over a 0, a k minus 1, I think. Just this. Right. So this is what? This is f of 0 plus, yeah, the sum. So in the end, I think right, f of, yeah, f of 0 is 1. Okay, there's some normalization here that we'll have to take into account. So let's see, but basically, you get f of 0 plus some 1 over a 0 a k from k yeah, so here will be k minus 1 from k equals 1 to n. Okay, so now let's see, right? So now let's see what happens. So if f has a non-constant solution, so you see the boundedness, right? So let's say that f is bounded is equivalent to say that this series is finite. So yeah. Yeah, so basically this is just a way to you know, you start from f0 and you write your values of f of n, and then, well, you see immediately that either this is, yeah, if this is bounded, that you can define f of n like this, and this would be bounded, and if not, well, if this diverges, then this f of n also has to diverge, unless we started with a constant function, which I think would just mean that this delta are all 0. Yeah, I think here we're secretly using this fact. Otherwise, you know, all the deltas would be 0, and so then f of n would be equal to f of 0, and then so the only solution would be constant. Yeah, so this is more or less. So in fact, here you don't just get what is the solution is, you know, don't just get exactly the fact that it is transit, but you get the probability, as you said, like, so basically you get the probability that you are going to arrive at 0 starting from some point. Yeah. Okay, very good. So maybe, yeah, I think it's good time for a break, so we can resume at like 11:15, I guess. Yeah.
I got the check. It's like obviously one step.
Okay.
The proof is easy.
Please.
So you have, okay. The twos gives you f of xn.
Mhm.
So greater than or equal to expectation of infinity, right? Which is equal to 1, right?
Mhm.
So that's the expectation for all this limit here. F of xn is equal to 1, but this is a martingale as well. It's a constant sequence, and this is equal expectation of x1, or any particular n really. So this is equal to 1. So this has to, and because f is less than equal to 1, therefore this implies that xn almost further.
I agree.
Okay.
Oh, very good.
I was thinking another like a way to say this. I mean, this might just be that, but is that like if it goes to like xn has to, if it's recurrent, then it has to go to 0 infinitely often, and all the other values infinitely often as well, right? So if it's non,
Say it again. Yeah.
so if it's non-constant, then like it has to go to, or sorry, xn has to go to 0 infinitely often, all other values infinitely often as well. So if there's some, if it's
But why?
what?
Why
It's
is that?
recurrent, right?
Yeah, but it's not irreducible, this Markov chain.
So then, okay, so
Because when you get to 0,
I mean, it is because you're on the n, right? So I think,
I'm saying this Markov chain is not irreducible, right? Because once you're at 0, you cannot get out of it. So
oh, we're not letting it go out of 0.
yeah, you're never going to get out of 0 because the probability of going from 0 to anything else is 0. Right. I mean, in a normal, in a usual situation, I would agree.
Yeah.
Like you would have a, yeah, exactly. Okay, so I think we can get started again. So So the next topic will be stationary measures, which are important in particular because when we have a random walk and the random walk eventually converges to the boundary, which we will prove in many situations, the hidden measure will be an example of such stationary measure. But in general, what is a stationary measure? So we need to start with some useful definitions anyways. Okay, so again, we have always G a group. So a metric space B is a G space if G acts on B by homeomorphisms so of course so there is a map from a homomorphism from G to the homeomorphism B. And remember, yeah, so we take the space to be metric for, for simplicity to make it not topologically too exotic, but the action here is by homeomorphism, not by assumption. So B stands for boundary. So whenever we put B, you have to think of it like that. And in fact, the most important examples for us would be the group SL2R or PSL2R, right, which is the group of isometries of the hyperbolic plane, well, acts by homeomorphisms on the boundary, which is, we can call it in many ways. It's a P1 of R, or it's basically S1. So again, the action inside is by isometries, but the action on the boundary is just by homomorphism. Okay, so in general, what is the definition of stationary measure? Well, a measure mu on B is mu stationary if, well, it's not invariant because there need not be any invariant measure, but it's invariant on average. So if you take G star nu, so you take nu, you act on G. So remember that the way you act on measures is by push forward. And then you're taking the average. So in general, for any measure on the group, we're taking the integral with respect to your measure mu, that is a measure on the group. Right. So this datum here is we start with the group G and a measure on the group. And so this is equal to nu. And okay, if G is countable, we can write it as sum of nu G star nu equals nu. Just because the integral just becomes a sum, right? Because the measure has some countably many weights. Okay. And in fact, the next definition is to say that a metric space, yes, so a G mu space is a pair of B and nu, where B is a G space and nu is mu stationary. So yes,
I understand that for applications, we want the action to be by homomorphisms.
Yeah.
But is the notion meaningless if you assume the action is by isometries?
no, it's not meaningless. But yeah, you very rarely find such an action. I mean, yeah. I mean, if you have an irrational rotation of the circle, that would be an action by isometries. I mean, yeah, I mean, it's very, very strong to have it by isometries, of course. Yeah, of course, the definition only uses the actions. Sorry? Yeah, exactly. So there would, yeah, it's too strong, right? So you don't want to preserve it at the distance. That's extremely rare. Yeah. So yeah, so the best example is the hidden measure. So it's like this. So you let X be a metric space. And the boundary X boardification of X. What does it mean? That is, boundary of X is topological space. So that X is dense in X union boundary of X. So you have some way to put some boundary here. So far, you don't need any. And suppose the G is a subgroup of the isometry group of X. So this acts by isometries on X. And suppose that the action of this extends to an action, so acts by homeomorphisms on the boundary. So in most cases where we have a boundary, this is the case. So we have a metric space, we have G acting by isometries, and then there is some way to define some boundary. And for this boundary, the group action extends to the boundary, but of course it extends not by isometries on the boundary, but it extends us by homeomorphisms. Okay? Okay, and now suppose that for some point inside and for almost every sample path, Wn O, the limit exists. The limit as n goes to infinity of Wn O exists in the boundary. If that is the case, then we have a G mu space. And let's prove that. Okay, so then we can look at nu of A, as I said, the probability that the limit of Wn O is in A. So again, this is the situation. You have a subset A, you have O, you have your walk, and your walk might or might not converge in A. So nu defines a stationary, a mu stationary measure on this geometric map. Okay, so let's prove this. So again, what do we have to check? We have to once again check that the integral of G star nu d mu equals nu. Right? So let's try to unravel these definitions. In fact, yeah. In fact, let's even assume that the group is countable to make it a bit simpler, so we can just take mu of G star nu. And now let's try to, we have to test in a set A. So A is the subset of the boundary. We have to test this. Okay. Okay, let's see. So what is this? This is the probability that the limit of W and O belongs to A. And what is this? Right, so this is a sum over G in G of mu of G of G nu, G star nu is nu of G inverse of A, right? So this is the probability that the limit of W and O belongs to G inverse of A. Right? Okay, let's think about it. What what are we doing here? Why is this the same? Well, we're isolating, it's like isolating the first step of the walk. So if you think about it here, what is this? So we're doing a walk of Wn. So remember that this is G1, Gn, right? So this is the probability of the limit. So G1, G2, Gn O is in A. But what if we condition on the first step of the walk? So the first step is this G1. What is this G1? Well, you see, we have the probability of G1 being whatever it is. And then once we condition on having G1 fixed, we are looking at, yeah, we can take G1 and acting by G1 inverse on both sides. So maybe let me write it even a bit. So okay, a bit in a even bigger. So this is the probability that G1 equals G. Let's say that times the probability, right? That G1, G2, G and O is in A, given that G1 equals G. So this is the full conditional. Yes?
Are we multiplying? Are we left multiplying?
Yeah, that's how it works. We always do that.
We just set up
Yeah.
I guess.
But that's the definition, yeah.
And in between the G1 to Gn minus 1.
That's right.
That's
That's right. No, you should be confused, but that's the correct. That's the correct set notation. Like that's the correct setup for which things work. Otherwise, they don't. Okay, so what's going on here, right? So okay, the probability that G1 is G is by definition mu of G. And now here, right? Okay, we are fixing G1 to be G. And so the first element is G. But now, since the action, right? There's this G action. So if G1, G2, Gn is in A, we can act by G inverse on both sides. So this is the same as the probability of G2 G and O to be in G inverse of A. Now you're basically just conditioning on the first step of the walk, and then you apply this G equivariance. And then you see, if you realize that, okay, sorry, the limit. So here there was a limit. There's always a limit. So you see, it doesn't matter because the G2 GIs are IIDs. They're Bernoulli process, so it doesn't matter if you start from the second. It's still the same process as starting from the first one. So this is the probability of hitting G inverse A. So this is literally sum of a G of mu of G, right, nu of G inverse A. So this is exactly this. Okay. So this is the most important example. So this shows that the heated measure is a harmonic measure, is a stationary measure. In general, there could be more stationary measures. So in general, it's not true that all the stationary measures are hidden measures, but in the cases that we're interested in, yes. Like what? Yeah. Yeah. That's right. In higher rank is more complicated, but in rank 1, yes. Yeah. Okay, so what else? So now we can look at existence of stationary measures. So just the existence of stationary measures is in the basic case. So if the boundary is compact, this is somewhat straightforward by classical functional analysis. So here's the most important lemma, is that if B is a compact, yeah, you see here's the metrizable assumption, compact and metrizable metric space, then yeah, there for any G mu, there is a mu stationary measure mu, which depends on this mu on B. And again, here the compactness is really important. And in fact, in some other cases that I worked on, this compactness doesn't hold. So that creates more complicated things. But for the classical case, like in the circle, for instance, okay, so well, maybe, yeah, I mean, this is a classic fixed point theorem, basically. Maybe we can see a few facts in classical analysis, in functional analysis. That's from functional analysis. So first of all, okay. So recall that. So you state let B be a compact metric space. Then we call C of B the space of continuous functions. And so this is a Banach space. With a subnorm. And any measure gives rise to a function here. So any measure on mu on B yields a function of psi mu from the space of continuous functions on B to R, which is given by integrating. So psi mu of F is the integral over B of F in D. And of course, this is a bounded function of psi. So nu F is bounded linear functional. This is because if you take the norm of psi nu of F, the norm of the integral is bounded above by the subnorm of B, certainly if nu of B is 1, which will be most of what we care about. And so we have the dual space definition would be CB star is the space of bounded linear functionals. Okay, and so the famous theorem here is the theorem of Ritz-Markov or Takutani, whatever. Is that indeed the space of Borel measures on a compact metric space are dual to the space of continuous functions, right? So let B be compact metric space. Then the dual space of functions, of continuous functions, this is the space of signed Borel measures. So what does it mean? It means that every time you have a functional which is bounded and linear on the space of continued functions, well, there is secretly not quite a measure, but there is a sign measure. So it's like a measure, it's sigma additive, but it could have either positive or negative signs. Okay. Very good. And then we can also define the Weak-Star convergence, which if you say we start at V be a normed vector space, then on the dual space, we can have a Weak-Star convergence. So then given a sequence psi n in V star, and which is the dual, we say that phi n converges weak star to phi if they converge on every vector. So phi n converges, put the half star here, if phi n v converges to phi v. for every. Okay, and then so in particular, if you have a space of measures, if you see nu n is a space on PB, so these are the probability measures on B. We say that nu n converges to nu. Sometimes we usually forget the star if for every f, which is a continuous function, the integral of f in d nu n converges to the integral of f d nu. So it's useful to think of measures as dual to the continuous functions, because every time we talk about convergence of measures, we're secretly talking about the pairing between measures and functions. Okay. The other final theorem that is useful from functional analysis is the famous Alaoglu-Banach theorem. So what does it say? Yeah, the unit ball, yeah, exactly. If V is normed vector space, then the unit ball in V star using the dual norm is weak star closed. Sorry, it's compact. Sorry, it's compact in the weak star topology. Yeah, remember that you have a norm of a functional is just the supremum of the norm of phi of V divided by the norm of V. Okay, so this is just to remind you what, yeah. So it's always useful to think of functions and measures as dual spaces to each other, in particular, because we're going to look at convergence of measures very often. And so this will come in handy. So given that we can prove the existence of stationary measures, right, before that, we need another lemma, which is very useful, is that if B is a compact metric space, then the space of probability measures, P of B, is also compact. Okay, so let's see how do we do this? Well, we basically leverage the Alaoglu-Banach theorem. Does anybody want to give it a try? Yeah, so probability measures are special elements in the dual to C of B, right? So we know that by Allaho-Glubanach, what do we have? We have that the unit ball in CB star is compact. That's right. That's right. So P of B is obviously a subset of CB star. And we just have to check that this is a closed subset. Why is it a closed subset? What are the conditions that define a probability measure in the dual? So these are all the functionals, right? So these are all the functionals on the space of continuous functions. And what are the properties of an honest probability measure? Yeah? That's exactly right. So it has two properties. So it's positive. So phi of f is positive for every f is positive. And the second one is that the total mass is 1. So for instance, if you apply to the characteristic function just the one function, this is 1. So in fact, this is in fact a cone in the vector space. And clearly, these conditions here pass to the limit taking the weak star convergence. Because if we test on every function, if you have a sequence of functions, these conditions pass to the limit. So this one is a closed cone. So it's a closed set of compact set. So it is compact. So it is compact. It's actually, note the following, that in fact, P of B is compact if B is symmetric space, if and only if B is compact. So because what happens, suppose you have a space which is non-compact, how do you produce a sequence of measures that does not converge? Yeah, basically that's the idea, right? It's like if you have a sequence of points that escapes, then you take the delta masses of those points, and those also escape. So that's basically the idea. Exactly. Okay, so we're almost done. So we can apply this theorem to give us the existence of stationary measures. And in the meantime, yeah, also it's good to review this because we will use it in other sections of the course. But so in the end, we can also define a convolution operator. So again, let B be a G space. Okay, then we have the following map from G times B to B. So this is the action, which starts from G and boundary point psi gives you G psi. This is just the action by homomorphisms. And yeah, we can define a convolution operator here. So given mu is a measure, is the probability on G, and nu is a probability on B, we can define the following. Define mu star nu, which would be a probability on B. And this could be, for instance, the push forward. If you want to be formal, you define it as the push forward of the product measure. So you have mu star nu, mu times nu. This is just a product measure. And then we push it forward by the group action. We'll get a new measure on the boundary. And we call this the convolution of mu and nu. Right? So in fact, the property is that the integral of f of g psi d mu g d nu psi over g times b, by definition, for every function, is the same as the integral of f of y d mu star nu of y. For every f, for instance, in every bounded f, for instance, on the bound. And anytime you can integrate, but let's see. Okay, so that's the convolution operator. And in fact, it's not so hard to see that a stationary measure is a fixed point of the convolution operator. So the remark is that nu is mu stationary if and only if mu star nu equals nu. You have to think about it, but basically, if you apply this to f a characteristic function of every set, you get exactly like that. Right? So, so if f is the characteristic function of a set A, right? You want to say that the characteristic function of g psi, then mu g, then mu psi, because the integral of the characteristic function of ay d mu star nu y. So this is mu star nu of A. Right? And this one is what? Right? So this is the integral over g of d mu g. And then you think of this guy. What is that? What is the characteristic function of g psi? Is the characteristic function of g inverse A. Right? So this is nu of g inverse A. So clearly, so the characteristic, so this one is the push forward. And so then this one is equal to nu of A. But this is if and only if nu is mu stationary. Okay, so we actually have time to give the proof of the lemma, which is somewhat a well-known technique. In fact, so the proof that of existence of stationary measures it's a classical fixed point theorem, in fact. So we want to show that there exists some measure nu in the probability space, in the space of probabilities for B, such that mu star nu equals nu. And the classic idea of such fixed point theorems is that you iterate this operator, the convolution operator, until you get a fixed point. But if you just iterate in a simple way, you might not get a fixed point. So you have to average once again. So define. So you start with any measure, like you knew 0, whatever measure. Then you set nu n as 1 over n sum over mu convolution k times with itself star mu 0. So k equals 0 to n minus. So it's important to take this average. Now, since the space of probability measure is compact, where there exists a sequence such that nu of nk converges to something. Right? And now the claim is that mu star nu equals nu. That this limit point of the Cesaro average is always a fixed point. Right? And why is that? Well, we have to check, right? So mu star of the limit over k of u over n over k, sum mu star I star nu from I equals 0 to n k minus 1. Yeah, you're shifting this over to inside the limit, and then it turns out that you have a telescoping series. So maybe we can finish the argument next time. It's not so hard at this point. Basically, you have this series, a plus 1 star mu 0. So the idea is that since this is a limit, so if you compare this with the original one, you get almost the same sum. So we're just off by 2 terms, and then when divide by nk, it goes to 0. Okay, maybe we don't want to rush it because we're out of time. So I'll finish this step, which anyway is more or less a standard way you prove fixed point theorems for operators that preserve a compact subspace. In fact, this is a special case of the Schauder-Tikhonov fixed point.
Can you also construct harmonic functions as fixed points of certain operators in a similar way?
This is a good question. Yeah, it's a good question. In principle, I can see that, but I have not seen it. Yeah, usually you construct harmonic functions are limits. But yeah, there is obviously this. I mean, there definitely is this averaging operator also on the space of functions, which is definitely due to this. But I guess I guess here you're using the compactness. Yeah. Okay, anyways, are there any questions so far? Okay, so then we can see each other on Thursday, I guess.